So what space is not used? Let's consider the one deep lane first. In the one deep lane, all the lanes are used, but the aisle space is of course wasted space. It is not used for storing products. So we said the aisle width is measured in pallet positions, and the number of pallets that is equal to the aisle width is A. And we also said because two lanes are opposite of each other, that we only count 50% of the aisle space for one lane. So if we use one lane, A over 2 is the wasted space for using the aisle. Now, how many aisles do we have in use in the one deep case? On day 1 we have 4 aisles, on day 2 we have 3 aisles, on day 3 we have 2 aisles in use, and on day 4 we have 1 more aisle. So in total we have 10 lanes in use, and for each lane A over 2 is the wasted, the unoccupied space. So the unoccupied area is given by the formula 10 times A over 2. How does it work for the 4 deep case? So for the 4 deep case, you see that we have 4 lanes in use. That means 4 times A over 2 is the wasted aisle space. And then we have 6 pallet positions, 1 on day 2, 2 on day 3, 3 on day 4, that are not used. So the unoccupied area days are 4 times A over 2 plus 6 unoccupied pallet positions. Now let's repeat the exercise for the 3 deep case. For the 3 deep case we have 5 lanes in total in use. So we have 5 times A over 2 as wasted aisle space, and there are overall 5 empty slots. Though the formula for the 3 deep lane to reflect the unoccupied area days is 5 times A over 2 plus 5. Now our next job is to draw these formulas in a graph. Recall that A was the width of our aisle, and the width is expressed in pallet positions. And of course we can have wider or smaller aisles. So now these formulas given in the column function, they describe a straight line, and in order to draw a straight line we need 2 points. So let's just take 2 arbitrary values for A. Let's say we take A equals 2 and another value could be A equals 6. The values are freely chosen from my side. Of course it makes sense to choose some values that give you round numbers approximately. So if I substitute A by 2 for the 1 deep case, then I get to the numbers 10, and if I substitute A by 6 I get to 30, because 10 times 6 over 2 is 30. I repeat this for the other functions as well. For example, for the 4 deep lane and A equals 6, I calculate 4 times 6 over 2 plus 6, which is 18. Okay, now I have for each function 2 values, and I can draw the straight lines, and the result looks something like this. On the x-axis we have the different values of A reflecting the aisle width, and on the y-axis we have the unoccupied pallet base. So as you can see, the red line is a line that reflects the one deep storage. And you see the y-axis, unoccupied pallet base, so higher numbers are worse. We prefer lower numbers. Yeah? We prefer low waste of space, of course. So given that we prefer lower numbers, the too deep storage is the best for values of a equals 1 to 4. And then starting with the value 4, you can see the smallest space is wasted for the 4 deep lane. That means as long as our aisle width is smaller than 4, we should go for 2 deep lanes, and if our aisle width is for some reason bigger than 4, then we should go for 4 deep lanes, under the assumption that we care most about the wasted space, and again under the assumption that we have this demand cycle of 4 units per 4 periods. Okay, but this gives you an idea how we can analyze this impact of honeycombing. And you see, of course, for large aisles, like at the value of 4, the 1 deep storage option wastes a lot of space, which is clear. And yeah, you see the 3 deep is not super bad compared to the others, depending on big aisle space, but it's never really the best. Yeah? So 2 deep or 4 deep, based on this input data, is the best aisle space, the best lane layout that wastes the least space.